and gentlemen, the second paper, formation of shape, molded, melt glowing, non-woven structure. This is a joint paper, but the presenter is Abdelfattah and Seyam. And please welcome Abdelfattah and Seyam.
I am presenting the paper, but we have a team here, group from the College of Textiles and one from the College of Engineering. His expertise is in robotic systems. And this collaboration led to direct fabric manufacturing. We can have a mannequin or a human standing on in front of a machine that sprays fiber, and I'm going to show you how it works. My colleague Charles Bush supposed to present the paper, and he was excited about coming to Egypt, but something happened to his wife, he had to stay home. So I got to do it, and that's why I'm doing many papers in this conference. This work is funded by ARO. MORI stands for Multi-University Research Initiative. We have 3 universities: North Carolina State University, Accra University, and Drexel University. We worked at NC State, which is North Carolina State University, and Accra, working on polymer. The Accra is good in polymer. We can develop polymers, new polymers. So the idea here was to develop polymers that has smartness with it. Smartness that can protect against chemicals or biological threats. It can absorb these threats if you wear the garment or wear the fabric. So it can absorb this chemical and make it neutral, so you don't hurt, you don't get hurt. Whoever wears the fabric doesn't get hurt. So we thought this way: if we want to have a protection, and you have smart polymers that have protection, if you take these polymers and try to do them the traditional way, cut and sew, you're going to, in fact, introduce weak points to the system. By having needles that go through the fabric, you're going to have holes, you're going to have tears, small, but enough to cause trouble. So the idea here is to directly form a fabric which has no seams. We're going to cover a human body with no seams, continuous spray of the fabric on the fibers on the body. So what we did here, we want to develop or combine 2 technologies. One is the melt glowing, and one is robotic. The melt glowing, how many of you are familiar with the term melt glowing? Anybody see what melt glowing means? Okay. This is, you're all familiar with extrusion, right? You know how we spin continuous filament yarns from melt. This is the same thing here. But what you do here, you spray the fiber, meaning you have an air. The fibers come from extruder as normal, and then the fiber comes out from the orifices, and then you have air coming parallel to the fiber that melt blown or below the fibers to a receiver. And the traditional way, melt blown is here for 30 years now. And the traditional way of using it is to produce sheets, fabric form of 2D, just like any fabric, sheet of fabric. And you collect it on a roller like you do your woven fabric. So why can't we take this now, and instead of making and then cut it and sew it, why can't we just spray it on the mannequin and form the fabric, form the garment? Melt-blown fibers are weak. They are not fibers that are designed to stand alone in the fabric and give you the functionality that you have in any fabric. Like here, I can pull here, I can stretch it, nothing is going to happen. Melt-blown is very weak fiber. The idea of melt-blown is to produce very small fiber. The smallest fiber can be as small as 1 micron. We have diameter distribution, but the small can be small as 1 micron. And the processing parameters can control the diameter. If you reduce fiber of 1 micron, I can cover your body, the entire body, with probably less than 50 grams of fibers. So it's lightweight. Also, when you have small fiber, you can have maximum surface. The surface that you produce. Imagine that you have a fiber as big as my finger. If you cut the fiber, not my finger, to 2, what you get? You're going to get more surface. You're going to create more surface. So imagine that if I can cut a fiber that big to thousands of fibers, you create more surface and you create more protection with lightweight. I'll tell you about this. This is not important now. So what we did, this technology reducing fabric 1 meter wide to 5 meters wide. This is a commercially available fabric. What we did, we had a special machine with only 3-inch die. You extrude fibers from a die, stumbling die, with orifices side by side. So you get line of fibers coming out from 3-inch. 3-inch, 7.5 centimeters. We wanted that small so we can spray the fiber. If we had it too big, the fiber is going to shoot out, right? So we want it small. So we got this machine, 3-inch, which is a melt-blown equipment, and then we got 6-axis robot. 6-axis means 6 degrees of freedom. I'm going to show you the robot and melt-blown in a minute. And this here you don't have to worry about. If we want to use PET, polyester, we need to dry the polymer. We don't want any oxygen there, so we have to dry. And ultrasonic was to bond the fibers together. But we found out we don't need to bond the fibers. Why we need the robot? The robot is to change the distance between the receiver, the mannequin or the body, which is going to receive the fiber, and the die. So if I have the die on the robot, I can move it like this. And it is well known that the closer you get to the robot, the closer you get to the receiver, fiber receiver, the stiffer the fabric is. You go back, you get the fibers develop, and you get more flexible fabric. So the distance between what you call a DCD, die to collector distance, affects fabric properties. We also found out a distance, a close enough distance will give you adhesion between fibers. So you don't need to bond them because the fiber coming already hot and built and molten, so they can stick together. So we don't need to bond them. If we move the mannequin and the robot, you can spray everywhere. I also, since the DCD, this distance, is affecting properties, so I can also produce a fabric with multi-properties. If I want a flexibility here, I need to go further apart. If I want some stiffness here for shape, like we do in our jackets, then I come closer. So I can design the entire fabric with properties that I'm looking for. Here's a robot. So what we did here, to integrate the melt-blown equipment is right here. This is a hopper which takes the polymer. We put the polymer there, and then it goes to the extruder, which is here. Then you extrude the fibers by screw that turns and push the polymer, molten polymer. Traditionally, the die is here. Normally, the die is here. So we put the die here. We want to move the die, so we have to make some flexibility between the extruder and the die. We split the die from the extruder, and we had two hoses, flexible hoses. One takes the polymer to the die, and the other one takes the air. And so we make the system flexible. This is the head of the robot. I had a video here, but it needs real player, and it's not on the machine, so you miss the fun. Anyway, you will get the point. Now, if you want to have a 2D fabric, you shoot the fibers to this cylinder, and when it rotates, you just take the fiber from here and put it down here on the roller. So it keeps rolling. So what we need to do now is remove this and put a mannequin in. And the mannequin is on axis. It can rotate around the cylinder. And we call this number 7 axis. So we have 7 degrees of freedom. I can rotate this at any speed. Constant speed, variable speed, whatever I want to do, I can program it to rotate 1 revolution or half revolution or quarter revolution at certain speed, and even 15 degrees at certain speed, the next 15 degrees at different speed. If you look at this point, if I'm rotating this at certain speed, the surface speed here will be higher than the waist, right? The surface speed here will be lower than the bottom here. So the amount of fiber is going to be lighter here, and here it is going to be thick, right? Because it's slow. So we need, if you want uniform fibers on the body, you need to consider the speed, the surface speed, not the rotation speed. So we have to control the surface speed momentarily everywhere. The rotation speed must be changed to get surface speed constant if you want. Now we want to demonstrate the system works. You need to know if you want to lightweight, you have to put uniform fabric. If I'm going to have non-uniform fabric, I'm going to have to increase the weight to cover the fabric, to cover the body. You don't want to have light piece on the fabric, so you have to spray more to cover it. So uniformity is very important in reducing the weight. So we have to do uniform fabric. We've done a lot of work on this. What I'm going to do today is just to illustrate for you how can we develop control algorithms that make the fabric weight constant as we desire. So we tried models. We tried 2D model and 3D model. And I'm going to explain this on the figure here. This is just what I said. You don't have to, I'll explain this here. The 2D model, I'm just explaining this on a cylindrical part with elliptical cross section. If you go to the mannequin or the human body, you can see you have ellipses. If you imagine cutting with a real cutting, you can see you have ellipses, right? So if we start spraying here, fibers coming from the die to the body, this is the side view, this is the top view, or front view and top view. So what we need to do here is move this vertically, start here, move it up. If you want another layer, you move down. And also, you have another degree of freedom, which is going back and forth, away from the mannequin. So DCD is this die to collect to distance. Right? So we call this 2D because you have motion, vertical motion, have here DCD. You have two dimensions. That's all what I put it, 2D for two dimensions. So let's see now adapting some models, what can happen with two models. What you see here with the x-axis, we have 15-degree intervals. So if you have 360 degrees around the body, you have 360 divided by 15, you get 24, right? 24. So number 1 is 15 degree, number 3 is 45 degree, and so on. This here, this part here, is the front of the mannequin, and this part here is the back of the mannequin. And this here is the side. Right? The side is here and here, and this is the front, and this is the back. This point and this point is the same, right? From the last figure, we done no correction. No correction means that DCD was constant. We did not do anything. We just moved the die up and down by the rollers to do two layers. As you see here, all these are two layers. No correction, you get this distribution. Why do we have this distribution? We have 3-inch die, right? And when you shoot here, this is less than 3 inch. So the fibers shoot out of this part to the middle. That's why you get high fibers. You get more fibers here. While you are spraying here, the fibers come through. So that's what happens. You get light here on the sides and heavy on the front and back. That's why we have this. So we thought that if we do DCD correction, meaning I'm going to keep the DCD constant. So when you have the distance from the front, you're going to have higher distance. When the mannequin turns, the distance will be closer. I'm going to move this away to keep the distance constant. It didn't help. Why didn't it help? Because closer is better. If you go here, when you spray, you have what we call splitting or flaring. The fibers go more than 3 inch. So if you go away, you actually make it worse. So you have to stay closer. Here, so we can see that we didn't improve much. We have 26% meaning it's not more non-uniform. The CV is the coefficient of variation of the weight. 23% is better than 26%. Fabric is more uniform here than here. So DCD correction didn't do any help. But linear speed correction, we had this mannequin rotating at constant rotation speed in this here, in this two here. Now we done linear rotation speed correction to make the surface speed constant, so you get uniform spray. So we have big improvement compared to 23. So this is a bit better. And with the two corrections, we got 16. So this is the best thing. You need to keep the distance constant, but you need to take care of the linear speed. Correct it to get constant surface speed. Now we thought that instead of keeping the die orientation like that all the time, we need to play with it. Make the die move. And if we make it move parallel to the surface, you don't get shoot out. Right? You get the fibers in the place you want it. So here's what we've done. We call this 3D. You have 2D, just like before, and this way here, this and this is the third D. So we have 3 dimensions, 3 parameters that I can play with. So here's what we did. We have 4 orientation. This one, actually 3. This one and this one are the same. So the sides will be the same and the front. So when this part comes to the die, this part comes to the die, you will get this. Right? When you have 45 degree, or 135, right? So when you have these sides, those 4 sides, you change the orientation. This one and this one are the second and third. So we have 3 positions that we decided to play with. Only 3 positions, we didn't change it continuously. And this is what we get. And this 1 layer. The other were 2 layers. And you got, if you do these 2 layers, the CV will drop more than that. Right? So the 1 layer, we were able to have 1 layer. We covered the entire body with about 45 or 47 gram per square meter. Okay? So we got better uniformity when we use the 3D. With this, I think we proved that we can make a fabric right on the body of human. Talking about mass customization, you may be able to do this here. You don't need to take measurements, right? But, like I say, this is made from polypropylene. Polypropylene fiber is very weak. This technology is 30 years old. Many fibers are adjusted to be processed on the melting point. Who knows? We may get. We already have done BET, which is strong, but still not as strong as what you do in real extrusion, the other extrusion. So if we are successful to make the melted load and the polymers adapt and make strong fibers, we'll probably be able to make fabrics on the body. You can do some fabrics. It's not going to be fabrics that you're going to walk in the street with. Maybe you're going to go swimming with. Whatever. Anyway, there's a lot of imagination that can take place here, and I think you probably got some ideas you can tell me about. By this, I finished, and I thank you for your attention.
There is time for one question. Anybody would like to?
Thank you, Dr. Seyam. I want to ask about the speed of the model. It's constant?
The
model.
Yes,
the American.
you can control it. You can make it as constant as you want, or you can make it variable. And we actually, one of the curves, one of the graph that I showed was done with variable rotation speed.
So we can slow the motion of the turn of the mannequin,
Right.
on the bottom and on the waist or something like this if we want thick places.
Right. If you want to have thick, that's a good idea. If you want to have more fibers here, you can slow the rotation speed so we get more fibers. So we can control the design where you want to put the fiber. More fiber here, more fiber there. The amount of fiber that you want to put anywhere can be controlled by the speed.
Excuse me, one more question. What about the surface? It's harsh or?
The surface is very soft.
Soft.
But please don't take the wrong idea. The melted blown fiber,
Still harsh.
speed.
Still.
You cannot use them alone.
Yeah.
The idea here is to put them with your cloth. This is for people who are working on threats where chemical and biological threats are there, like police, army, people working with chemical, cleaning chemicals. You can have this in the system. So you will have woven fabric or knitted fabric, and you spray this on the top.
Can we use it as a shirt for anti-shoots or something like this?
With the shirt,
Yes.
not as a shirt.
Yeah.
Alone it can't work because it will tear easily. It's weak fiber.
Because I think the non-woven fabric is against the shoot of bullet or something like that.
Oh yeah, you're talking about
As a protection.
no. This is not. You could use it to insert. We have some idea of while I'm doing this fiber on the mannequin or on whatever, I can do one layer and I can make spaces. I can put what whatever I want around the body and then spray again.
Yes.
So you can put whatever you want. You can put here
Sheets of
sheet,
steel or something like this.
exactly. What we call this ceramic or steel or whatever, or other fibers or fabric.
Thank you very much, Dr. Seyam.
You're welcome. Thanks.
Thank you, Dr. Seyam. Wonderful new technology. I'm sure certain time will come when it will be very successful.